Hello guys. In this video, I'm going to talk about the bias and variance in classification models. My specific goal with the video is to show you how to do a plot to visualize the presence of either high bias or high variance, which are both kind of undesirable situations when we are training machine learning models. I think this video will be more valuable for those of you who have at least a basic understanding of what bias and variance are. Because in this video, I don't want to spend time kind of explaining you what these two concepts are. So I'm assuming the viewer has at least a basic understanding of these two concepts. Again, my focus in the video will be to show you how to do a plot to visualize high bias and high variance situations. All right, perfect. So I created a Python notebook in Colab for the video, and I will share a link to this notebook in the video description. The notebook already includes all the code needed to run the analysis because I really want to focus on explaining the outputs from the code, explaining the machine learning ideas. So I didn't want to spend time like writing code as I was doing the video, okay? All right, so perfect. So let's start by importing some of the functions and libraries that I'm gonna need in this analysis, all right? So let's start by doing that. And done. And then after that, let's go ahead and explore the data that I'm going to use. The data come from the study done by these two researchers, okay? And the study was about the classification of sonar signals using a neural network, okay? And this is specific citation to the paper published by these two authors with this study, okay? So you can Google it and you'll get you'll be able to get a PDF of the study, okay? Now, the goal of the study was to train a neural network to discriminate between sonar signals bounced off a metal cylinder and those bounced off a roughly cylindrical rock. In case you're wondering, a sonar signal is a sound wave that is transmitted into water and then reflected back to a receiver, all right? So that's the goal. That was the goal of the study. A little bit more about the data. The data contains 111 patterns obtained by bouncing sonar signals off a metal cylinder at various angles and under various conditions. And also, it also contains data about 97 patterns obtained from rocks under similar conditions. Okay, if you're wondering what a pattern is, a pattern in this problem is just simply an instance, okay, a record. So patterns refers to just records, observations, okay? So in this data, we have a total of 111 plus 97, 208 patterns or 208 observations, okay? All right, so each pattern is a set of numbers in the range from 0 to 1, and each number represents the energy within a particular frequency band integrated over a certain period of time, okay? In short, guys, so for each record, for each observation, there are 60 features. So for each observation, for each pattern, they recorded 60 numbers. So we have 60 features in this study, okay? And each feature takes a value between 0 and 1, okay? All right, and in terms of the outcome variable is the label associated with each record, which is either R, meaning like the signal is coming from a rock, or M, meaning that the signal is coming from a metal. So this is a binary classification problem with two classes, R and M, okay? And the outcome is the last column in the data set, okay? Now, the data can be found in this CSV file, Sonar CSV file, which is available on GitHub, specifically in that URL. So that's the URL that we're going to use to access the data. And with that URL, we can invoke the read_CSV function from pandas and read that CSV file into a data frame, into a pandas data frame, okay? And there are no column names, so that's why header is none. Okay, so we don't know the names of any of the 60 features. Right? We don't need to. All right, so let's take a look at the data frame, and sure enough, we have. Let me see this. Go up. As I told you, we have 208 entries. So we have 208 rows, 208 observations, 61 columns, so 60 features and one outcome, right? And notice that all the features are float, or they have float data types, or they are numeric, okay? Numbers between 0 and 1, right? And the last column, which is the target, has data type object. So it's categorical because it takes values M and R, okay? So it's a categorical column. So that's why this is a classification problem, okay? If you take a look at the last column, okay? The last column is the one with index -1 to see the classes and get a value count. You will confirm what I told you earlier. So we have 111 signals coming from from metals, and 97 signals coming from rocks. Okay, perfect. All right, so let's continue. In terms of pre-processing, we only need to do one step. So we need to pre-process the data to split the data. Why do we need to split the data? Remember, guys, in machine learning, when you're training a model, you need to split the data into 3 data sets: training, validation, and test data sets. Now, as some of you might know, there is an alternative to that. If you want, you can split only into training and testing, no validation, okay? And if you do that, what you can do is you can use the training data to apply cross-validation, all right? If you do that, so if you only split into training and testing, the test faults from the cross-validated data will act as multiple validation data sets, okay? So in this video, I will split only into training and testing, and then I will use the training data to get multiple validation data sets via cross-validation, okay? So both alternatives are correct, okay? Either train, validation, test, or train and test, and then apply cross-validation with the training data, okay? One thing that I wanted to mention, just in case you notice at the end of the video, that I never use the test data here, and that will be correct. I will not use the test data, guys, because remember, the only goal of the test data is to obtain a final and unbiased evaluation of your chosen model. So if you want to have an evaluation performance, an unbiased evaluation performance of the model that you have chosen as the best one, you use the test data for that, okay? I'm not going to do that. I don't want to obtain any final evaluation of any model, so that's why I'm not going to use the test data. However, I still need to do the split into training and testing because I do need the training data. I need the training data to apply cross-validation, okay? Just keep that in mind in this specific video. I'm not going to be using the test data, okay? Because I don't need to come up with the final evaluation of any chosen model, okay? All right, enough talking. So let's do the split. To do the split, I always like to first create a variable storing the data frame with only the features, okay? So I'm getting, using that piece of code, I'm getting all the columns but the last one, okay? Remember, the last one was the target. So this will give me from Sonar DF all the columns with all the rows, but the last column, okay? So that would be all the features, okay? And you can take a look at that and notice that, sure enough, we have 60 columns, okay? And the last one is not the target, so the target was excluded. I like to do that. I also like to, I like to do all of this before splitting, okay? I like to create a variable to store the target, okay? So now I'm getting from the Sonar DF only the target. So index -1, that means the last column, okay? And after doing that, I go ahead and usually invoke the train test split function from scikit-learn. And obviously that function allows me to split the data into training and testing, okay? The first 2 arguments of that function are data frame with the features, the series with or array. It depends. Both are valid. Series or array with a target. The third argument is the test size 0.20. That means 0.20 means that I'm devoting 20% of the data for testing and obviously 80% for training, okay? Random state equals 1. What I'm doing there is I'm setting the seed equal to 1. Why am I doing that? Because I want to control the randomness of the splits. And what that means is that anyone using this notebook will end up with the same train and test split. And if you end up with the same train and test split, you're going to end up with the same results that I'm going to get. Okay, so I want to make sure that my results are reproducible. So like everyone gets the same results I'm going to get, okay? And this final argument is kind of optional, but I think it's a good practice to do. So when you set the stratify parameter to the variable stored in the target, okay? What you're doing is you're saying, okay, when you do the split, I want the class distribution in the whole data set to replicate to both the training data and the test data, okay? So that's what I'm doing by setting a stratify to white. Again, not mandatory to do, but kind of a best practice, okay? Anyway, so let's run the split. And after that, we're gonna have xtrain with a data frame with the training data and the features. Xtest would be a data frame with the test data and the features. Ytrain would be a series, a pandas series with the train data and the target, and ytest would be a panda series with the test data and the target. Okay, good. We're gonna use this when we fit or train the models. Okay. All right. So let's move on to the next thing to do. So let's go ahead and assess. Let me show you how to assess the bias and variance of machine learning models with different regularization strength. So I want to train, as you will see, 3 machine learning models with different regularization strength, and I will show you how to assess the bias and variance for these different models. Okay. Specifically, I'm gonna train 3 logistic regression models. One with minimal regularizations, small regularization. Another one with an intermediate level of regularization. Okay. And the last one with a strong regularization. Okay. And this is very important, guys. Okay. For each model, I will obtain 2 metrics, the training error rate, which is the error rate on the training data, and the cross-validation error rate. And this is key, guys. The comparison, remember that, the comparison of these 2 metrics for a given model would be the key to assess the model's bias and variance. Okay, so by comparing the training error and the cross-validation error for a given model, I will be able to assess the presence of either high bias or high variance. Okay. All right, so let's go ahead and train model number 1. So the model with minimal regularization, okay? Model number 1, logistic regression with minimal regularization. So how do we control regularization? By controlling the strength, the regularization strength parameter, which is lambda, okay? And lambda is the penalty parameter in the cost function. So to remind you of the importance, not the importance, but to remind you of the role of lambda, I created this slide. Let's go over this slide briefly, guys. So to understand the impact of lambda in a regularized cost function, okay? Okay. If we are using an L2 regularization, which is the kind of regularization I will be using in this video, this is the cost function, guys. This is the cost function. And the cost function will be the loss function, okay? This first part, the loss function across all n training observations. So the loss functions sum across all training observations, n training observations, okay? Plus lambda times the sum of the square feature weights, or you can also say the square of the feature coefficients, all right? And that's the cost function, all right? Now, one thing I wanted to mention is that on purpose, I did not specify the formula for the loss function, right? I only called it loss, okay? Because, explaining the formula for the loss function will require a kind of separate discussion. So I just wanted to call it for this video loss function, okay? Anyway, so what's the role of lambda in this cost function? Well, lambda controls the weight or importance given to each feature, okay? A large lambda means that most features will be given little weight in the model, okay? And if that happens, only a few features will have an impact in the model's predictions, okay? That's what a large lambda means. In contrast, a small lambda means that most features are given a large weight. So with a small lambda, most features will have an impact in the model's predictions, okay? Now, as practitioners, as machine learning practitioners, we need to find, let's say, a good lambda, okay? A lambda that gives us a balance in terms of how to distribute the weight or the importance across all the available features, okay? And as you will see, the good lambda that offer us that balance could be found by kind of inspecting certain patterns in the training and cross-validation errors. So I will show you later that um, these patterns that we can observe in the training and cross-validation error um, will be explained by the trade-off between bias and variance. All right. Okay. So now that we understand the role of lambda in the cost function um, in logistic regression, let's go ahead and go back to the notebook. All right. Um, Now we have a little bit of an issue here, guys, because in scikit-learn we cannot directly set lambda, but the inverse of lambda. So we don't have lambda available in scikit-learn. We have a parameter called c, and c equals 1 over lambda. So that's all right. Even if we cannot set up lambda, um, given this formula, we know that if we want a specific lambda, we can solve for c in this formula, and then from the desired lambda, we can set the needed c uh, related to a lambda. Okay. Okay. So for model number one, as I was telling you, we need minimal regularization. Okay. So relative to lambda, as we discussed earlier, minimal regularization means a small value, specifically a value close to zero. Okay. So I want to set lambda to 0.001 to represent minimal regularization. And if I want that to be lambda, then based on this formula, C will be 1000. Okay. Okay. So I'm creating a C value of 1000 to specify minimal regularization. Let's go ahead and create that. And now I'm going to fit a logistic regression model with that C value, okay? To fit the logistic regression model, I'm going to use a pipeline because to apply logistic regression, we must standardize the features. And in scikit-learn, the, the best practice is if you want to apply a machine learning model, and before doing that, you need to do some pre-processing steps, like, for example, standardization. You should do it. So it's not mandatory, but the recommendation is to do it as part of a pipeline. Okay. So that's why I am here defining a pipeline to standardize the features and then to apply logistic regression. Okay. And inside the logistic regression function, I'm specifying that C will equal this value that I defined here. Okay. One more thing, and this is what that's why I include this comment. When we apply logistic regression, the logistic regression function in scikit-learn, by default, an L2 regularization is applied. That's perfect because that's what we want, right? I told you that I wanted to apply L2 regularization. Okay. Okay. So let's define the pipeline. And once we define the pipeline, we can use the pipeline to feed the desired logistic regression model to the training data. And to that, we use the feed method. Okay. And I'm going to store the result of that feeded method in this variable, logistic regression model number one. So that will be the train model number one. Okay. Okay. And all right. So once we have our model number one with minimal regularization, we can use it to do what I wanted. Remember that we are going to compute two metrics, right? Two metrics. So the training error rate and the cross-validation error rate for each model. Okay. So let's go ahead and do that. Let's use model number one to predict the training data so we can get the training error. Okay, so I'm going to store the predictions of the training data in that variable. And then I'm going to invoke the accuracy score because what I want to do is to get the error, I'm going to get the accuracy first. Because remember that the error rate is 1 minus the accuracy. So if we get the accuracy, we can easily get the error rate, okay? So I'm going to get the accuracy by using the accuracy score function. And the accuracy score function takes two arguments. So a variable with the actual values of the target, that's why train, and a variable with the predicted values of the target, that's why train predict model one, okay? And we are obtaining this for the training data. So that's why you see the train um, word specified in these variables, okay? Okay, so that variable will store the accuracy, and then once we have the accuracy, we do 1 minus the accuracy to get the error, and let's take a look at the error, and the error is 0. So perfect performance, okay? So model number one has a perfect performance flawless performance in the training data, okay? All right. How about the cross-validation error for model number one, okay? To get the cross-validation error, we need to apply cross-validation. I'm going to apply cross-validation using the cross-validation score function. But before doing that, we need to, I mean, we don't have to, but it's customary to um, define the strategy you want to use to apply cross-validation. And I'm going to define the strategy to use cross-validation using the k-fold function. With the k-fold function, I can specify that to apply cross-validation, I want to use 10 folds or 10 splits, okay? I want to shuffle the data before applying, before creating the fold. So before creating the 10 folds, I want to shuffle the data and random state equals 1, control the randomness of the created fold. So I'm going to create 10 folds randomly, right? By splitting the data randomly. I want to control that randomness, and I'm going to do that by using random state equals 1. Remember, by controlling the randomness of the folds, anyone using this notebook will end up with the same cross-validated result, okay? Which is what I want, okay? All right, so that will be my cross-validation strategy. And now I can apply cross-validation score. That cross-validation score is the function that allows to apply actually cross-validation, okay? It takes a few arguments. The first argument is what model are you applying cross-validation on? So we're applying cross-validation on model number one, the one that we just got, okay? And then we need to specify the training data again. We need to specify how are you going to evaluate the cross-validation results. What metric are you used to evaluate the cross-validation results? I'm gonna use the accuracy because remember, from the accuracy, we can get the error. Our goal is to get the cross-validation error, but once we get the accuracy, error is just 1 minus the accuracy, okay? And the cross-validation will be guided by the cross-validation strategy that I defined here, okay? When we apply cross-validation score, we actually get, as you will see next, 10 cross-validation results, okay? Why 10? Because we defined 10 folds, right? For each fold, we end up with a cross-validation result. In this case, we are using the accuracy as the metric to evaluate each cross-validation result. So we're getting 10 accuracy scores, okay? So for each split, for each fold, we get a cross-validation accuracy. And remember that when we apply cross-validation, the final cross-validation output is the average of the cross-validation results obtained from each fold, right? Remember that the final cross-validation performance metric is the average of the performance we get for each cross-validation iteration, okay? So to come up with the final cross-validation value, we need to get the mean of these 10 values, right? That's what I'm doing next. So I'm getting the mean for these 10 values, and that would be the cross-validation accuracy for model number one, okay? So this will be the cross-validation accuracy for model number one. And once we get the accuracy, we can get the error by saying 1 minus the accuracy, okay? And what's the cross-validation error for model number one? 0.265. So whereas on the training data, model number one did perfectly, so no error. With cross-validated data, it doesn't do that well. We got a 0.26 5 error rate, okay? All right, so let's repeat the same analysis for the other models. So model number two would be one with an intermediate regularization. So for intermediate regularization, I'm going to use a lambda of 1. And lambda 1 means that C is also 1, okay? So we can represent intermediate regularization using a lambda 1. And lambda 1, if we saw in the formula that I showed you earlier, will give us a C of 1, okay? And we repeat the same steps again, but in this case, using intermediate regularization. So we create a new pipeline for this situation. We feed that pipeline to a training data, and that will give us logistic regression model number 2. And then we repeat the same thing. We use model number 2 to predict the train data. Then we compute the train accuracy for that model. Then the train error, and the train error is 0.048, so 4.8%, okay? So whereas model number 1 has a 0 error on the training data, model number 2 has a 4.8 error, okay? How about the cross-validation error for model number 2? We repeat the same steps again, but using model number 2, and we get that the cross-validation error for model number 2 would be 0.217, so a little bit smaller than the cross-validation error for model number 1, right? Model number 1 gave us a cross-validation error of 0.265. Model number 2 is giving us a cross-validation error of 0.217, so smaller, okay? So model number 2 is doing better with cross-validated data, okay, than model number 1. And model number 3 means strong regularization. So remember, relative to lambda, strong regularization means a large value. So I want to set lambda to 1,000 to represent a strong regularization. Setting lambda to 1,000 means setting C to 0.001, okay? So that's the C I'm going to use to represent strong regularization. Same thing, so a new pipeline to represent that strong regularization. And then with that pipeline, we're going to get model number 3, okay? And then let's get the training error for model number 3, and the training error for model number 3 will be 0.22. 8, so even higher. So this is the highest training error we are getting, right? Because model number 1 was 0 for the training data. Model number 2 was 4.8. And now model number 3 is giving us an error rate in the training data of 22.8. So it's the largest, okay? How about cross-validated error for model number 3? Same thing, same procedure. And then we get a 0.28. 0.28 cross-validated error. Okay, so even higher than the cross-validated, cross-validated error that we got for model number 2 and model number 1. Okay. All right. So 0.26 for model number 1, 0.21 for model number 2, and now for model number 3, the cross-validated error is 0.2893. So model number 3 is giving us the highest error for both training data and cross-validation and cross-validated error. Okay. Okay. So guys, at this point, we are kind of ready to do the plot to detect the high bias and high variance situations. But I really want to show you, before doing that, I want to show you the impact of lambda on the model's coefficients. Remember that earlier when I was discussing this slide, I told you that, large lambda means a strong regularization, which means that only a few features will have an impact on the model's predictions, right? And I told you that small lambda means weak regularization, which means that most features will have an impact on the model's predictions, right? So I want to show you that, okay? So, and to that, what I'm going to do is, we have 60 features, right? We have 60 features. So instead of displaying all 60 features for all 3 models, that would be a really, really long output. I have decided to show you the top 20 largest coefficients in absolute value. So instead of showing you all 60 coefficients, I'm going to show you the top 20 largest coefficients in absolute value. Remember this, guys. The largest the absolute value of a coefficient, the more important the feature with that coefficient for the model is, right? Remember that. Largest absolute value means that feature, the feature with that coefficient is more important, okay? Okay, so to simplify all of these computations, I decided to create this function, and that function will do the following. Given a model, given the specification of a model with a specific regularization strength, it will return the top 20 most important features. So meaning like the 20 features with the largest absolute value coefficients, okay? So let's go ahead and run this code cell to define the function. And now let's invoke that function on each of the 3 models to see the top 20 features for each model, okay? All right, so this would be the coefficients for model number 1, which is the one with minimal regularization, so with a small regularization, okay? There you have it. And let's notice a few things. So these are the top features, right? Notice that the first most, let's focus on the absolute value, okay, this column. The first most important features all have absolute values above 10, right? Like when you look at the first most important features, their absolute value are above 10 for all of them, okay? But even if we scroll down and we kind of take a look at, we start kind of getting closer to the features with ranking close to 20, right? Even in that case, all the coefficients are above 5. So keep that in mind. So top top most important features for model number 1, coefficients above 20, I'm sorry, above 10 in absolute value. But even when we get close to ranking 20, the absolute value is above 5, okay, for all the features. Let's see what happens with model number 2, which is intermediate regularization. Well, look at the top features now, the coefficients for the top features, okay? Now the coefficients or the weights, the importance, if you will, of even the top most important features have reduced, right? From being above, from the weights being above 10, now the weights for the top features is 1 point something, 1 point something, all right? And when we look at features, the features with ranking close to 20, now the weights are around what, 0.5? Whereas before the weights, even for this feature, was above 5, okay? So we have seen a reduction in the weights importance of all the features, okay? And when we take a look at the third model number 3, wow, now even the top features, guys, have low weights. Even the top features have low weights. And if we scroll down, we start seeing like really, really small weights. And we can kind of expect that if instead of only the top 20 features, we explore the coefficients for all features, probably the least important features, okay, will have coefficients very, very close to 0, right? I think we can expect that. Like if we're saying like the coefficients are so small for the top 20 features, if we get close to 60 to the least important features, some coefficients will be very close to 0, meaning like with with strong regularization, we expect that some features will have coefficients very close to 0, which essentially means that these features will be excluded from the model because, if the coefficient of a feature is close to 0, that means that that feature is not really considered in the model, if that makes sense, okay? All right, guys, so what do we conclude after observing the coefficients, okay, for the different regularization strength, okay? Well, this is what I want you to remember. With low regularization, like model number 1, okay? With low regularization, model number 1, many features have, let's say, sizable weights, which means that many features are used by the model. Now, think about this. If many features are used by the model will tend to be more complex. And that's what I actually want you to remember. Low regularization means many features are important in the model, and we will tend to end up with more complex models, okay? Low regularization, many features are important, and that means that we will tend to have more complex models, okay? Now, as we saw with model number 3, kind of the opposite happens, right? A strong regularization, which is model number 3, means that fewer features are important in the model, and it could even mean that some features are kind of essentially excluded from the model, right? Because I told you that with a strong regularization, like the least important features will have coefficient very close to 0, so they will be almost excluded, okay? So remember this, strong regularization, fewer features are important in the model, and that means that we're going to end up with less complex models, okay? And sometimes we can even say that these less complex models are kind of simplistic models, right? Because let's say if in a model only very few features are important, then that model might be too simplistic, okay? So keep that in mind. Strong regularization, fewer features are important, less complex models, and in some cases, depending on the strength of the regularization, some of these models might be really simplistic, okay? So keep these ideas in mind as we explore the final plot now, okay? All right, let's explore, I'm sorry, the plot, uh, visualizing all of this. All right, now in this plot, what I'm going to show you is the training error and cross validation error for each of the 3 models. And remember that each of the 3 models was obtained with a different lambda, with a different regularization strength. Okay, and as you will see, a plot like this will allow us to spot high bias and high variance situations. Okay, so let's run the code cell and let's take a look at the plot to understand it. Okay, I want to mention a couple of things from here. The first thing is, remember, guys, so what matters in machine learning is not the training error, is the cross-validation error or the validation error. Okay, so I'm going to say cross-validation because we apply cross-validation to get the validation error, but we can also say validation error. So in machine learning, what matters is the validation error, okay? Not the training error, because what we care about is the, let's say, the generalization performance of the model. So how well the model predicts unseen data. So how well the model generalizes to new data. Okay, so data that was not used to fit the model. You know what I mean? That's the generalization performance. And to evaluate the generalization performance, we need to use the validation data. Okay, because the validation data was not used to fit the model. So again, in machine learning, the important metric is not the training. Like the metric that we use to evaluate the quality of the model is not the training error, but the validation error. Okay, remember that. And another thing that I wanted to mention was this horizontal dashed line, guys. When you are trying to understand the bias and variance trade-off in a given problem, it's useful whenever possible to have what they call in machine learning a reference level performance. Okay, reference level performance is just let's say the level of error that we hope to achieve or the level of error that we desire to achieve. And guess what, guys? In this problem, we have a performance level as a reference performance level. Okay, why? Because these authors, remember the authors of the study. Okay, um, they apply a neural network, right, to do this classification. So we just apply we just apply logistic regression, right? But they apply a neural network, and they reported their best result as a 15% validation error. Okay, so when you read the paper, the best that the neural network was able to do was 15% error on the validation data set. Okay, so that's why in this problem we have that reference level of performance. Okay, and that reference level of performance is useful to evaluate bias. Okay, so when you have that reference level, you should use it because it will facilitate the evaluation of bias, not variance, but bias. All right, let's try to understand this plot and how it maps to high bias and variance situations. So let's start by um, notice that first on the x-axis we have the lambda values. So but in our problem we only use three lambdas, right? 1,000. These are these two data points, right? 1,000, we used 1, and we use 0.01. So it's kind of hard to show the 0.01 in the x-axis, but that's okay. So this one right here is lambda 0.01, okay? This is 1, this is 1,000. And then on the x-axis, we have the error rate, okay? And the orange line would be the cross-validation error, blue line would be training error, and as I told you, that horizontal line would be the reference level. All right, so let's take a look at the first situation. So what is happening when lambda is 0.01? Remember, when lambda is 0.01, that's a small value of lambda. That's, low regularization, meaning like many features are important in the model. So that means the model will be complex, right? Well, what is happening is that for a complex model, we can see first two things. There's a big gap between the training performance and the cross-validation performance. The training performance is much better than the cross-validation performance. Okay, we get a cross-validation performance above 25%, and the training performance was 0%. So perfect performance. So low, um, small regularization, complex model, huge gap between training performance and cross-validation performance. And that, guys, indicates, that's the first indication of a high variance situation, okay? So high variance, like a model exhibiting high variance will show this pattern where it will do much better on the training data than on the validation data. And that's what is happening right here. Okay, that's the first sign of a high uh, variance model. So the first model, model number one, the one where we obtain with a small lambda, is giving us a high variance situation. Why? Because what I told you, we see a big gap in the training and validation performance. And actually, what happens is that the training performance is much better than the validation performance. That's the first indication. The second indication is that this does not always happen, but it happens quite often. The second indication of high variance is that the training performance is much better than the reference performance. So the reference performance is 15%, and and with this model number one, the training error is 0%. So it's kind of the second indication that we have a high variance situation. So to sum up, model number one is giving us high. Uh, Model number one is exhibiting high variance because the gap in training performance and cross-validation performance, and also because the training performance is uh, too good. You know, it's too good. It's just much lower than even the reference performance. Okay. All right. Now let's go to the other extreme. So the model number three, the one we obtained with lambda 1000. That means lambda 1000 means, remember, strong regularization, where only fewer features are included in the model, right? And that means that the model is not very complex and it could be even simplistic, okay? What is happening here, guys? Well, notice that both the training performance and the cross-validation performance are worse than the error rate. So even on the training data, the model does worse than the reference performance. Okay, that is the first sign that this is a high uh, bias situation. So the first sign uh, that we are in the presence of a high um, bias model is that the performance for both the performance on both the training data and the validation data are worse than the reference performance. And that's what we are observing. The performance on both the training data and validation data are worse than the reference performance. And the second indication, because you need to put both things together, the second indication is that we don't see that big gap in performance between training data and cross-validation data. Okay, so if we put both things together, because we don't see a big gap between training performance and cross-validation performance, and because for both training data and the cross-validation data, the performance is bad. Why are we saying that it's bad? Because it's way above the reference level. Because of that, we can claim that model number three, the one obtained with lambda 1000, has high bias. Okay. And then, what happens with the model with intermediate level of regularization? Well, here it's kind of we don't have the same level of bias and variance, but we don't have resolve. Like we cannot claim like this model has like good bias and good, like low bias and low variance. Okay, that's not true because first of all, there's still a gap, right? So we still see a kind of sizable gap in performance between training and validation data, right? So we still see some variance, okay, and we still see some bias because the cross-validation performance, which is what matters, it's still kind of far from the reference performance, right? The reference performance is 15%, and the cross-validation performance for this model is above 20. So I think it was 21%. So it's still way above the reference level. Okay. So because we still see a big difference between the cross-validation performance and the reference level, and because we still see a gap between cross-validation performance and training performance, this model still exhibits some bias and some variance, but not as these two other models. Like in this model, there's a high variance, and in this model, there's a high bias. In this model, both issues have improved a little bit, but still they are still evident. Okay, so to sum up, guys, um, and this is something that happens very often. So models with low regularization, okay, uh, meaning like they will be complex models. Like low regularization means the model would tend to be complex. They will um, they will tend to exhibit high variance, okay? Like this one where we can see, remember, high variance means big gap between training performance and cross-validation performance, and the training performance is much better than even the reference level performance. And what it's also common is that models with strong regularization, which will be kind of models that are not very complex, kind of simplistic models, they will exhibit high bias, meaning like um, the performance of those models will not be good. So the performance of those models in both training data and cross-validation data will be way above the desired performance. Okay, and that's the way you will do a graph like this to detect situations with high bias and high variance. All right. Okay, guys, so that's all for this video. I hope you learn about bias, variance, and how to detect them, and how to map high bias and high variance to the regularization strength of the model that you train, okay? Okay, so thank you for watching. See you in another video. Bye.